So last class we kind of finished going over the composite of continuous functions, or a composition of functions, where if we broke it down enough to individual functions that were combined, if those individual functions were continuous, then the composition was continuous. And this is kind of where we left off. And now we are going to move on to something a little bit more visual. The intermediate value theorem for continuous functions. Sounds all fancy and crazy, but give it a chance. If f of x, okay, we have a function here, and here's a graph of f of x. Goes like this, goes like this, goes like this. Okay? So just pay attention as I explain this. If f of x is continuous, I can draw that without lifting up my pencil. That's continuous. On some closed interval from point A to point B. Okay? They're saying when I draw this graph in this interval when x is equal to A to when x is equal to B. So here's A and here's B. We have drawn f of x from where x is equal to A to where x is equal to B, all right? Nothing out of the norm there. I'm just interpreting this as we go. Picture to words. So, if f is continuous from A to B, which it is, then for any point C, there is a value for that function. F of C. If you take that value of x that we call C here, this is where x would equal C, and we put it into our function, we're going to get some real number. It can't be undefined. How can it be undefined if it's continuous? That means there's a point at every spot in x. So if I pick any of those x values, you're going to get a point with the corresponding y. There's no pole here. There's no asymptote here. There's no, what do they call that? Was it a sinusoidal? Remember there's no jump discontinuity, removal discontinuity. Infinite is the asymptote. Now, what was that one? Was it sinusoidal? It's like a sin, or what was that? No, oscillating. Oscillating. Thank you. We said at the same time. The oscillating thing here. That is a perfectly great function. That kind of looks a little like an f, which means, oh, Miss Donna, look at this. It almost looks like an integration sign, which is part of calculus, which we've got to learn derivative before we get to integration, which, anyways. All right, so does that make sense? Like, look at, if I pick some point between A and B, it could be any one of these points. I happen to pick this one right here for C. Okay, if my function is continuous, that means all these are points, right? There's no holes or breaks, correct?
Yes.
Okay, then at my point C, there has to be a value. There has to be a point here. There has to be. If there was a point there, then the function wouldn't be continuous. This whole thing starts out, if it is continuous. Yeah. I mean, if you kind of understand it, I mean, it makes common sense. Now, let me do it without letters and with numbers, because, hey, that's what we do. If I have a set of axes here, and we'll go 1, 2, 3, 4, 5, 6. That's 1, 2, 3, 4, 5. Okay, and this is 0, 0. We know that, right? 0, 0. Now, if I draw any function E, okay, E of x, because, you know, f always gets a lot of play. So let's do E of x, shall we? And I do something that kind of looks like this. It goes like this, like this, like this. I don't know, like that. If I say that my function E from when x is 5 to when x is 1, it is continuous. I don't care what happens smaller than 1 or more than 5. I don't know, maybe there's an asymptote, there's a hole. Who knows? Who knows? So, I gotta stop. So, if this is continuous, that means at every point where 1 is 1, there's a y value. Okay, 1, 1, right? At 2, might still be 1. shouldn't it? At 3, maybe it's 2 is my y value, correct? At 4, when we gather that, maybe it's 4, and at 5, maybe it's 5, whatever. Any point I pick between here is going to have an outcome, isn't it? That's all it's saying. Is if it's continuous, every point has to have an output. Every input has to have an output. Every x has to have a y. Because if every x didn't have a y, then it would have something like a hole here. You would have a hole there, or an asymptote, or an oscillating thing. Simple. I really over-explained that to death. Beyond me. But how you guys do it, correct? He's got it. He's got it. All right. Now let's do some basic algebra. Because this is what makes you guys feel comfortable. This is your home base here. So let's do algebra. Is there any real number that is exactly 1 less than its cube? Compute any such value accurate to 3 decimal places. Okay, so is there any real number exactly 1 less than its cube? So this statement here is telling me there's an equation. I'm setting 2 things equal. Okay? Is there any real number? So I know x is going to equal my real number. Okay? Is there any real number that is exactly, that's something the equal sign, this is my x, 1 less than its cube? If x is the real number, 1 less than its cube. That means I cube it and subtract 1. Compute any such value accurate to 3 decimal places. How can I do this? Plug it in where? Yeah, well, why wouldn't you just put it in the graph? What am I looking for in the graph? What am I looking for in the graph? There's 2 ways I can do it in the graph. If I'm looking for the 0, which is also the solution, which is also the... Well, I know you would have to do both sides to find is if the solution, the roots, the 0, the x-intercepts. If I want to search for the x-intercept, so I plug that in as it is. You can, but then you got an x on both sides. I won't even do that. Look it. Well, there are 2 ways to do this. What I would suggest is, what happens if I subtract x from both sides? 0 equals x cubed minus x minus 1. If I graph this, the x-intercept is my solution, isn't it? And guess what this graph is right here? That's the graph of this. Right? Sillies. But I would need to find out my x-intercept here. Now, I said there were 2 ways to graph this. Instead of bringing my x over, I could have put this in y1 and put this in y2. If I graph 2 functions, the answer is not, it's not the x-intercept anymore. It's where they would intersect. So you can do this one of 2 ways in the graph. Since the notes give me this cubic function set equal to 0, that's what I will do with you guys here. All right, turn this on. Y equals, it's clear. All right, seconds plus, let's clear this whole thing out because pre-calc use a lot of calculator today. So if I go to y equals, I'm going to say x cubed, okay, minus x minus 1. And if I graph this, I get this thing right here. Okay? I get this right here. Our answer is our x. There's only one answer right there. And I do this with both time. And how do I do that in a calculator? I do what to find it? Seconds Okay, I want calc, which is in blue, above trace. So I hit second trace. Okay, they get the calc menu. I want to calculate the 0. Now remember, the calculator is telling me I need to be left of the bound I'm trying to find. So if my little spider dude moving, left of that is obviously right there. That is down and to the left, so I hit enter. And you'll see it put this little arrow here. Okay? Now the calculator is telling me, okay, now I want the right side. I want to go right of where my 0 is. So I just move to the right of that. Now I'm up and to the right, and I hit enter one more time, and you see this second little arrow popped up. And why we say you need to make a bow tie? Because we have our bow tie right there with our dot in the middle. If you do this and it is not a bow tie and they face opposite, you will get an error. Okay? So if your bow tie is not, if those arrows aren't pointing to each other and they don't look like a bow tie, you've reversed your bounds and you'll do an error. So now look, I did my right, I did my left, and now it's telling me what? Guess. You want me to guess? Yeah, that's why I'm doing this. Hey, enter one more time. Bang. And it gives me my x value right here. Now, how do they want my answer? To the third decimal. So if I do this here, my answer would be x equals 1.325. Thank you. That rounds up because the number after it is a 7. Okay? And that's here. And you would say approximately because we rounded, didn't we? It's not equal exactly. It is approximately 1.325. Okay, so why don't you guys figure out this next one on your own? Is there any real number exactly 2 more than its cube? Compute any such value accurate to 3 decimal places. Okay, I'll give you a couple of minutes. Yeah. Okay, do you want to do it in the order?
Yeah.
Absolutely, come on. One of the Adams sisters. That's one of the Adams sisters.
You already know?
All right, show us what you got.
All right. Yeah, I got to talk with it?
You don't have to, I'll talk.
All right.
Unless you want to talk.
Nope.
Okay. Perfect. She has x equals x cubed plus z. I'm joking, it's a 2, I know it's a 2.
Yo.
Okay, so go ahead, you keep on working. Any real number exactly 2 more than its cube. X is your real number, and you want to make sure that it is exactly, which means equal, to 2 more than its cube. That's taking your x, cubing it, and adding 2. Okay?
Thanks for explaining.
Okay, not a problem. So she is going to go. Do I need to calculate or no?
Yeah.
Okay. She's going to put, she's not going to set it equal to 0 and then find the x-intercept. She's going to actually graph y equals and then graph both of them separately and see where they intersect. Back in the day when life was easy, we graphed 2 straight lines. The answer was where they crossed, right? Well, the answer will also be where these cross. Very good. And the worst, I don't want to say the worst, but the most common place for people to make mistakes is when they put types up in the calculator. It's crazy. There's y equals x. And look, we crossed once. Now, instead of picking the 0 option, I don't want my x-intercept. What option do I got to pick when I go to that calc menu? So it's second trace. Pretty obvious. 5 for intersect. Now, the beautiful part about this is you don't have to make a bow tie. You just have to get close to your intersection. Get close to your intersection there. Okay, now just hit enter 3 times. Bang, bang, bang. There it is. So why don't we drag this out? Bam. Now, why don't you write your answer to 3 decimal places for me, please, for seconds.
Correction.
I will make a comment on that. There you go. X is approximately equal to negative 1.521. Exactly. And if we're wondering, Did I do it the same way this way? I did. If you moved your x over and you grabbed just one function and wanted to figure out where it crosses, now look at this. We're gonna look at that. This is actually -1. This is -2. So right here, what do you think is that value? It's the same value, isn't it? So that's approximately -1.521. And you guys told me, yeah, that's almost halfway in between, which that is almost 1.5, isn't it? So I mean, it works out perfect. Doesn't matter. There's always more. There are always more than one way, because there's ways. There are several ways, I should say that. But I like to say 1 and 1. There are often more than one way. There is often more than one way to get to one answer. I don't judge your English, kids. I just judge your math. Okay? But there's always more than one way to get to one answer. All right? And there you go. That's it. Thank you very much.